How does the monthly loan payment amount get calculated? What are the finance and math concepts behind it? The answer lies in a formula few people know, one that makes lending and borrowing possible. It's called the amortization formula. It might look complex at first, but by the end of this video, you won't just understand it. You'll see why it's so powerful. M is your monthly payment, the fixed amount you pay each month, covering both principal and interest. P is the principal, the total amount you borrowed from the bank. R is the monthly interest rate, your annual rate divided by 12, always expressed as a decimal. N is the total number of payments. Just like we did in my previous video on how loans work, this formula takes the loan amount, the interest rate, and the total number of payments to calculate the fixed monthly amount you'd have to pay over time. It's the core of how banks structure loan repayments. But where does this formula actually come from? This isn't just a random equation. It's built on core finance and math principles. Each formula represents a key concept that comes together to form the amortization formula. Let's start with the most fundamental one, the time value of money. The time value of money says that money today is worth more than the same amount in the future. Why? Because if you have money now, you can invest it and make it grow. Reversed, this becomes discount, retracing the growth from invest. Mathematically, we calculate the present value of a future sum using this concept. Now, let's apply this to a real loan example. Every month, you make a payment, but since these payments happen in the future, their actual worth today isn't the same. Each payment needs to be adjusted back to today's value. So, we apply our present value formula to every payment, adjusting them based on how far in the future they are. The first payment is discounted the least, while later payments, further in the future, are discounted more. This process of bringing future payments back to their value today is called discounting. And this is the foundation of how banks determine your loan payments. So far, we've been using the monthly payment amount as the future value in our formula. But remember, this video is about the amortization formula, the formula that actually calculates this monthly payment in the first place. That means we don't actually know these amounts yet, not in the way we need to for the full calculation. We're going to figure them out step by step. But before we move forward, take a look at these numbers. Do you notice a pattern? This pattern is the key to unlocking the full amortization formula. It's tied to something called geometric progression. A geometric progression, or GP, is a sequence of numbers where each term is obtained by multiplying the previous term by a fixed value, called the common ratio. Usually, the common ratio is written as R in GP, but since we're already using R for the interest rate, we'll use G instead to avoid confusion. If the common ratio is greater than 1, the sequence grows. If it's between 0 and 1, the sequence shrinks. This is exactly what we see in our discounted loan payments. If we look at our discounted values, we can see they follow the same pattern. This confirms that we have a geometric sequence with a common ratio. Now, to calculate the total value of these payments, we need to find the sum of this geometric sequence. For a finite geometric series, we use its summation formula. Let's apply this to our case. And now, solving this, we get a total that's slightly off from the original loan amount. That's because of small rounding differences in our calculations. But in reality, this should round to exactly the original amount. Now, we return to our three formulas. The middle one represents the present value of annuity. This formula is simply a combination of the two concepts we just learned. Let's break it down. We know from the time value of money that the present value of a future sum follows a specific formula. Now, let's apply this to multiple future payments. If we have several payments, each made at different times, we calculate the present value of each one separately. Adding them all together gives us the total present value of these future payments. Since every term includes future value, we can replace it with M, the fixed monthly payment. Now, we can express the total present value as PVA, the present value of annuity. And since each term has M, we can take M out as a common factor. This leaves us with a summation formula. Now, let's focus on what's inside the parentheses. If you look closely, you'll see that this forms a geometric progression. Let's bring back the discounted values from earlier. Just like in the formula, we can factor out M, our monthly payment, from that example. What's left inside the brackets is called the discounted payment factor. This factor only depends on R, the interest rate. If we sum the discounted values, we get a total that might not be what you expect. And if you thought this should be equal to the number of payments, you'd be wrong, because this is the discounted factor sum of a decreasing geometric progression, not just a count of payments. Now, let's analyze what's happening here. This expression starts with a first term, and by comparing two adjacent terms, we get the common ratio. Using the formula for the sum of a finite geometric series, we plug in our values. We substitute the first term. Then, we substitute the common ratio. Now, this expression represents the sum of the entire discounted series. If we bring back our three original formulas, we can see what's happening. The time value of money formula and the sum of a geometric progression merge together to form this new expression. Now, let's put these two formulas side by side. On one side, we have the present value of annuity formula. On the other side, we have the sum of our geometric series. At first glance, these expressions look different, but they are actually the same. By simplifying the right side, we can see it transforms into the present value of annuity formula. But here's the big reveal. This present value of annuity formula is actually the amortization formula itself. The only difference? It's just rearranged to solve for M, the monthly payment. By transforming this equation, we arrive at the exact formula used to determine your loan payments. And with that, we've uncovered the true foundation of the amortization formula. Now that you understand how this formula is built, the next step is seeing how it fits into the bigger picture of loans. If you want to see how the entire loan process works, from borrowing to repayment, check out my previous video where I break it all down in depth. Thanks for watching.